Hi everybody, welcome to part 2 of chapter 6. Today we're going to start with Balmer and Rydberg. They were two scientists who studied the emission spectrum of hydrogen. Especially Balmer, he studied the emission spectrum of hydrogen in the visible region. So Balmer studied the emission spectrum of hydrogen. Now hydrogen is the simplest emission spectra we can look at because it only has the one electron in the ground state. If you recall, the emission spectra happens when electrons are excited. They're given some sort of energy, and so they get excited and jump to higher energy levels. But being excited at those high energy levels is not very stable, and so they immediately fall back down to lower energy levels, emitting that energy that they had absorbed. And usually the energy that they emit is in terms of photons of light, and if it happens to be in the visible spectrum, then we'll see it. So let's write that down real quick. So electrons absorb energy and jump to higher energy levels. Which we call the excited state. When they are not excited, we call that the ground state. So they go from the ground state to some sort of an excited state, some sort of a higher energy level. Then they emit the energy. As photons, which are packets of lights, as they fall back down. So I'd like you to stop the video and wear your diffraction grading glasses again, and turn on the spec tube with the hydrogen. Make sure that all the lights are out. If you see any continuous rainbows, that's from the outside white light. We're looking for specific lines or discrete lines. You should be able to see 4 colors from the hydrogen spectrum. So stop the video for a minute and look at that real quick. Okay, welcome back. So you should have seen 4 lines. They're distinct lines with hydrogen. One of them is red, one of them is green, one of them is blue, and one of them is violet. I honestly, for me, the green and the blue kind of blur together and give me like a teal color. So I only really see 3 colors, but a lot of people can see all 4. So the 4 colors are red, green, blue, and then there's also a violet. Now the ones that we see from the hydrogen, that's called the Balmer series. So the Balmer series is the only visible portion of the emission spectrum. And that's where n final is equal to 2. So what does that mean? Remember that we have different energy levels. So I'm going to draw the lines that represent the energy levels here. And remember that the energy levels get closer and closer together as you move farther away from the nucleus. So this is the first energy level, n equals 1, n equals 2, 3, 4, 5, and 6. So the electron, the ground state for the electron in hydrogen is in the first energy level. But if you excite it somehow, so if you heat it up, if you shine a light over it, so if you give it some sort of energy, it will jump up to a higher energy level, to an excited state. So it could go up to the second energy level, the third energy level, the fourth, the fifth, and the sixth, and so on. In this case, in the case of hydrogen, it only goes up to the sixth energy level. And if you take physical chemistry in college, that's the third year of chemistry, you will do some calculations to figure out which jumps are allowed and which jumps are not. So which jumps actually really happen and which ones don't. So for now, we're just going to say that the electron in hydrogen can only jump up to the sixth energy level. So once it reaches the sixth energy level, so it could go up to second, third, fourth, fifth, or sixth. In any of those, it's excited, so it's not stable, and so it can fall back down. And so when it falls back down to the second energy level, that's where you would see it in the visible region. So for example, it could go from the sixth energy level down to the second, or from the fifth energy level down to the second, or from the fourth to the second, or from the third to the second. Now, if it makes any of those four jumps, we will see it in the visible region. Now, can you tell which one is which? Which one is the violet, which one is the red, which one's the blue, and which one's the green? You should be able to tell based on the amount of energy. So if you look at the jumps here, you can see that when it goes from sixth energy level to the second energy level, that's the most energy that's being emitted, followed by the fifth to the second, followed by the fourth to the second, and then finally third to the second is the smallest amount of energy. So if you compare that to the colors, we know that violet, out of those four colors, has the most energy, followed by blue, followed by green, and then followed by red. So you can actually assign the colors. So this jump is the violet, this one is the blue, this one's the green, and then this one is the red. Now, these are not the only jumps or emissions that those electrons can do. Maybe instead of going back to the second energy level, maybe it goes all the way down to its ground state where it goes to the first energy level. When it does that, that's called the Lyman series. And so let's draw a picture of our energy levels again here. So that's n equals 1, 2, 3, 4, 5, and 6. So again, based on some calculations and observed data, we know that one electron in hydrogen can only go up to maximum of the sixth energy level. And so when it jumps back down all the way to the ground state, to the first energy level, we call that the Lyman series. And so here's one possible jump from 6 to 1. You could go from 5 to 1. You could go from 4 to 1, 3 to 1, or 2 to 1. So there are 5 possible jumps. Now compare these in energy to the Balmer series. Would these have higher energy or lower energy than the Balmer series? You should be able to tell that these have higher energy being emitted, because there's a big gap between the first energy level and the second energy level compared to the other ones, for example. So you could tell that that's a much bigger jump than this one, for example. And so the light being emitted here, the photons from those emissions, have higher energy. So where in the spectrum would that be? That should be higher energy than violet, so that should be in the UV region. So I'm just going to draw a couple of lines here, and that would be our UV region. Now, alternatively, instead of the first energy level or the second energy level, maybe it only jumps a little bit less. Maybe it only goes to the third energy level. So if it goes down to, let's say, the third energy level, so the final energy level is 3. F stands for final, by the way. Let's draw them again. Here's 6th, 5th, 4th, 3rd, 2nd, and 1st. So again, highest jump that the electron and hydrogen can jump would be the 6th energy level. So here the options are going from the 6th energy level to the 3rd, or the 5th energy level to the 3rd, or the 4th energy level to the 3rd. And so that is called the Paschen series. Now again, let's compare the energies. And so if you compare the energies here being emitted, those are much smaller energies than those, which are smaller than these here. And so these would correspond to something that has a lower energy on the electromagnetic spectrum. And so lower in energy than red, that would be like in the IR region. So I'll put a couple of spots here for the IR. So if it happens that it's in the visible region, we see it as colors. If it's in the IR region, we don't really see it, but we can feel it. IR feels like heat. And if it's in a higher energy in the spectrum, then, you know, it's in the UV region, and we don't really see it. We probably don't feel it. We can maybe detect it somehow, but we don't really, we're not really able to see it or feel it. Now, in the past, on the AP exam, they expected you to know, to memorize the Balmer series and which jumps corresponded to which colors. I would not expect you to memorize the colors, but I would expect you to know or to be able to figure it out just like we did. So if you were to see a jump like that, you should be able to figure out that that would have higher energy than a jump like this one, for example. And you should also know that violet has higher energy than blue. So if I tell you I get a blue color and a violet color, and one jump is N6 to N2, and one jump is N5 to N2, you should be able to match them, for example. So you should be able to problem solve as opposed to memorize. Like I said in the past, that you had to memorize the Balmer series. That's where the final energy level is number 2, and you had to memorize the 4 colors and the 4 jumps. I don't expect you to know that. I would say just know that the Balmer series in the visible region. I don't expect you to memorize that the Paschen is the IR or that the Lyman is the UV, but again, if I tell you N final is 1 versus N final is 2, you should be able to tell that the jumps here would have higher energy, so you should be able to match them to UV compared to visible, for example, and so on. So be able to problem solve rather than memorize, basically. All right, let's move on to the next page, Niels Bohr. If you remember, Niels Bohr was known for his Bohr models. In biology, you used to draw Bohr models where you would have the nucleus should be really small and dense with the protons and the neutrons in the middle. And then the outside, you have these shells, the energy shells, that contain certain amounts of electrons. So the first energy level takes 2 electrons, for example, second one takes 8, and so on. Which we agree on all of that for the Bohr model. However, in chemistry, last year, we never really drew Bohr models because we don't really agree with them anymore. We agree with the quantum mechanical model, which says that those electrons are not in these set paths or orbits. However, we still do know that those electrons have certain amounts of energies. And that's what's so great about the Bohr model, and it matches up with the periodic table really well. And so really the biggest contribution that Bohr gave us was that he said that you can calculate the energy of an electron and its energy level. So you can calculate its energy level. And he gave us an equation to calculate the energy of an electron and its energy level. However, problem is you can only use this equation if it's mono-electronic or monoelectric. What does that mean? Mono means one. Electric comes for electrons. So that means you can only have one electron. So that really only applies to hydrogen, which has one electron, or maybe helium plus, so helium with an electron removed, or lithium with 2 plus, or beryllium with 3 plus, and so on. So only for one electron. So only for hydrogen and monoelectric atoms. If you have more than one electron, then that gets really complicated because of the repulsion between the electrons, and so this calculation doesn't work anymore. So let's look at his equation. So his equation says E sub n, so this is the energy for an electron in a certain energy level, so the lowercase n stands for energy level, is equal to negative. Now, there is no negative energy, you know that. What does negative mean in terms of energy? It either means it's being emitted, it's energy that's being emitted, or that it's attracted to something. And so in this case, we're talking about the one electron in the atom, and so there's a force of attraction between it and the proton in the nucleus. And so that negative basically is an application of Coulomb's law, which just shows that there's an attraction. So let's write that down real quick. So this negative here application of Coulomb's law. Do you guys know what a Coulomb is? It's a unit of charge. And so Coulombic forces, for example, mean charge is attracting. Positive and negative charge is attracting. And so on. So Coulomb's law talks about the attraction or repulsion of charges. And so we're talking about two oppositely charged particles attracting. And so if there's a force of attraction, then there's a negative charge there, or not negative charge, but just a negative sign there to show that. R is Rydberg's constant. So this is named after the scientist Rydberg, who studied the emission of hydrogen, the emission spectra of hydrogen, and so they wanted to honor him. It is 1.0968 times 10 to the 7th per meter, or you have the conversion for it for per centimeter. I doubt that you would use this. You'd probably use this one. Actually, you don't even need to use that. This equation, by the way, is on your green sheet, as well as E equals h nu and C equals lambda nu. Those are all on your green reference sheets. The value for Planck's constant and the speed of light constants are also on the green sheets. So I highly recommend that when you do your homework, you use the green sheets so that you're familiar with where the equations are, which equations are given to you and where they are, and where the constants are, so you don't have to memorize them, or you don't have to spend a lot of time during the test or during the exam looking for them if you need them. So we have the negative showing the attraction between the electrons and the protons, the R, which is Rydberg's constant. H is another constant. Do you remember which one it is? Yep, that's Planck's constant, the 6.626 times 10 to negative 34th joules per, joules times seconds. And then we also have another constant, which is C. Remember, C is the speed of light. 3 times 10 to the 8th meters per second. And then we have Z squared. So let's talk about Z squared for a second. So Z in chemistry is the atomic number. So Z equals the atomic number. Which the atomic number is, if you remember, the number of protons, right? Which is also known as the nuclear charge, because it's the charge of the nucleus. Remember, the nucleus has protons and neutrons. Neutrons are neutral, protons are positive, and so the charge that's in the nucleus is basically a number of protons, or the nuclear charge. And so do you remember Zeph? Z with a little EFF as a subscript? That's the effective nuclear charge, because Z by itself is the nuclear charge, which is the atomic number, which is the number of protons. So on the AP exam, they will only give you hydrogen. And so Z for hydrogen is just 1, only has 1 proton. The atomic number is 1. On my test, I will also just ask you about hydrogen unless it's extra credit. And so on the green sheet, I believe that this equation does not have Z squared in it. And you don't need Z squared if it's hydrogen, because 1 squared is just 1. And so you can just kind of remove it from the equation. And so that's the equation on the green sheet. If I ask you about, another monoelectric atom like He plus or Li2 plus or Be3 plus or B4 plus, I guess, you can keep going, then you will need to put in a different number there. So for lithium, the atomic number would be 3. For helium, it would be 2, and so on. So just watch out for that. And again, if anything, it would be extra credit. And then the last number here is n squared. So n is your, remember, lowercase n is your energy level. So if the electron is on the first energy level, then n equals 1. If it's on the second energy level, then it's 2, and so on. Now, there's so many constants here. We have R, we have H, we have C. And so they combined all these constants. Instead of, looking up 3 constants every time you have to use this equation, they combined all of these and came up with this number. So basically, this equation is the one that you would want to use instead of putting in all these different variables. And this equation, again, is the one on your green sheet, but it's missing the z squared because it's assuming that you're using it for hydrogen, so z squared would just be 1. All right, so how do we use this equation? Let's try it. So it says, what is the energy level, what is the energy of an electron in hydrogen where n is equal to 1? So this is a ground state electron. So another way to ask this question would be, what is the energy of a ground state electron in hydrogen? You'd say, well, in hydrogen, the ground state electron is on the first energy level, so you would use this equation, and you would use 1 for the energy level. So you'd say E sub 1, so the energy level, or the energy for the electron in the first energy level for hydrogen is equal to negative 2.178 times 10 to the negative 18 joules times z squared, that's 1 squared, because the atomic number for hydrogen is 1. N squared is 1 squared, because the energy level is 1. And so it's just basically negative 2.178 times 10 to the negative 18 joules. And so what that means is this is how much energy that electron has in that first energy level. And again, that negative is telling you that it is held there by an attraction to the nucleus. All right, let's try the next one. It says, what is the energy level? What is the energy of an electron in hydrogen where n is equal to 2? So that's an excited electron that went to the second energy level. So you'd say E sub 2, so the energy of an electron in the second energy level is equal to negative 2.178 times 10 to the negative 18 joules times 1 squared, because it's hydrogen, so the atomic number is 1. But then on the bottom, that's 2 squared, because it's the second energy level. So I'll let you plug that into your calculator. You should still get a negative answer. So I got negative 5.45 times 10 to the negative 19th joules. Okay, what if we didn't want to know just about an electron just there? What if we wanted to know about an electron that is absorbing energy to go to a higher energy level, or emitting energy to jump down to a lower energy level? So you have the electron in one energy level and it's going to a second energy level. So to calculate that, you would find, the energy in the first position, the energy in the second position, and subtract the difference. And so let's try to come up with an equation to calculate that. Now, you don't have to do that. You can just calculate them separately like we did here. So if I wanted to see what it would do from the second jumping down to the first, I would just subtract these two from each other. So you calculate them separately and then subtract them from each other, or we can come up with an equation to combine kind of these two together. So instead of just the energy at a certain energy level, I want the difference in energy, or delta E. And difference in energy is always final minus initial. So your final energy level minus your initial energy level. So let's come up with that equation here. So it's going to be delta E is equal to negative 2.178 times 10 to the negative 18 joules, and then 1 over n final squared minus 1 over n initial squared. Again, that 1 we're assuming is for hydrogen. If this was a different substance, so like Li2 plus, for example, then this would be 3 squared, and this would also be 3 squared. So just watch out from that. So let's try to apply this second equation that we have here. We want to calculate the frequency, wavelength, and color of the emission where the electron falls from the 6th energy level to the 2nd energy level in a hydrogen atom. So that's a hefty question. Let's think about what's happening here. So we are going from the 6th energy level to the 2nd energy level. So the electron is excited in the 6th energy level, it's falling down to the 2nd energy level. We want to calculate a whole bunch of stuff. We want to calculate the frequency, the wavelength, and the color. Now, this is a jump, either an emission or an absorption. In this case, which one is it? Yep, that's an emission because you're going from high energy level to low energy level. So that's going to emit energy. So we can't find the frequency and the wavelength right away. We have to find the energy first, and we can use the Bohr equations that we've been using to calculate that. So what I would do first is I would say, okay, well, delta E, the change in energy for that emission, how much energy is emitted by that electron as it goes from the 6th to the 2nd energy level. So 6 to 2 is going to equal to negative 2.178 times 10 to the negative 18 joules, and then 1 over final energy level. Watch out, it's final minus initial. So final energy level would be the 2nd energy level. So that's 2 squared. That's a squared there. Minus 1 over the initial energy level, which would be the 6th energy level. So 6 squared. And so go ahead and calculate that. I got negative 4.84 times 10 to the negative 19 joules. Now in this case, what does that negative mean? In this case, that negative means that energy is being released. How do I know that? Because it's emitting the energy. So let's make sure that we take note of that. So the negative means energy released or emitted by the electron, which makes sense because it's going down. All right, so the reason why we calculated the energy is so we can calculate the frequency and the wavelength. Which one can we calculate first? We have to calculate the frequency first because we have an equation that links between energy and frequency. We don't have an equation that links between energy and wavelength yet. So even if they didn't ask for the frequency, you have to find the frequency first before you find the wavelength. So let's do that. Our equation is E equals h nu. So the energy, E, is 4.84 times 10 to the negative 19 joules. That's what we just calculated, is equal to, and in this case you don't have to put the negative in because you can't have a negative frequency. So, you know, obviously Planck's constant is positive, so you can just plug the absolute value for the energy in there. You don't need the negative. Again, the negative just tells you which direction the energy is going. Is it emitted or absorbed? So Planck's constant is 6.626 times 10 to the negative 34 joules times second, and then nu is what we're solving for. And nu ends up being, I'll give you a minute to put in your calculator. So nu is 7.29 times 10 to the 14, and the units are per second. Your joules and joules cancel, and you take this number divided by this number, so it ends up being per second. So that's one of the answers we were looking for. Then we want to also calculate the wavelength. So now that we have the frequency, we can say C equals h nu. Or I'm sorry, C equals lambda nu, not h nu. That's a lamp. So C is the speed of light, 3.00 times 10 to the 8th meters per second is equal to lambda, which is what we're solving for, times the frequency, which we just found, 7.29 times 10 to the 14th per second. If we look at our units, the per seconds cancel and we end up with meters, and so lambda in meters is 4.11 times 10 to the negative 7th meters. We also wanted the color, whether it's in the visible spectrum or UV or or infrared, or if it is in the visible spectrum, then what color it is. So to do that, the easiest way is, I think, to remember it in nanometers. So you can convert that. You'd get 411 nanometers. And so if you remember the chart that we had, the Roy G. Biv with green being about 550, and then for every color you add or subtract 50, then that's pretty close to 400, so that's close to the violet color, which actually matches if you look at the previous page of our notes. We said that the transition from the 6th energy level to the 2nd energy level, that's part of the Balmer series, and that has the highest energy in the Balmer series, which would correspond to the violet color here. So there are our answers. All right, I hope you have a wonderful day, and we'll continue our notes later.